Electrician program. This is chapter 12. Again, this is from the text of Modern Electrician Wiring, 9th edition. The lessons are written by H.N. Holzman. The lessons are edited and narrated by Hector Vladimir. Chapter 12, Branch Circuits and Feeder Service Design. The objectives for this chapter are to calculate branch circuit loads, determine the number of branch circuits for a house, explain non-coincident loads, calculate feeder and service loads, balance the loads in a 3-wire system. Some of the technical terms encountered in this chapter are branch circuit, demand factor, electrical load, feeders, non-coincident loads, and service load. Designing a safe and efficient electrical system is a responsibility that an electrician cannot take lightly. The system must be large enough to handle the loads that will be placed on it when the home is new, as well as when it's 20 years from installation. To ensure a quality electrical system, you must calculate the loads, determine the safe number of circuits to install, and select the proper conductors and equipment. Branch circuit design. Just as a tree has many branches growing from its main trunk, a well-designed electrical system has many branch circuits growing from the main service panel. To divide the load, the electricity entering a building is distributed into branch circuits. A branch circuit is a separate electrical path, independent of other electrical paths in the building. It draws its current from the main service panel and is protected by its own OCPD, that's overcurrent protection device. It serves one or more outlets for receptacles, switches, or fixtures. Figure 12-1, as you can see on the screen, is a schematic of a main service panel with branch circuits radiating outward. The result is an electrical service that is divided. A failure of any one circuit does not disable any other part of the system. Branch circuit load calculations. An electrical load is the amount of power required for a branch circuit, feeder, or service. The load requirement of each of these segments of an electrical system must be calculated before determining the number of circuits and the size of the conductors, OCPDs, and devices to install in a residence. Many branch circuits and feeders have utilization equipment that will not be used at the same time. Therefore, a total load on these circuits may be reduced by a percentage called the demand factor to create a lower electrical load. Throughout this chapter, you will see the examples of how and when the demand factor may be applied. The total of all branch circuit loads can be calculated after you know the square footage of the living space, the number and size of any large appliances, and the largest size of any non-coincident loads. The following sections will explain how you can use this information and the rules of the NEC to quickly calculate various types of loads that may be found on a branch circuit. General lighting load calculations. Although the NEC refers to this calculation as a general lighting load calculation, this load also covers small appliances, laundry units, bathroom requirements, and most receptacles throughout the home. The NEC Table 220.12 specifies the number of volt amperes for each square foot of building. This table relieves you from having to account for each light fixture, kitchen appliance, and piece of audiovisual equipment. For dwelling units, that number is 3 VAs for each square foot of living space. See figure 12-2. To calculate the general lighting load, first take the outside dimension or the outside dimensions and calculate the square footage of the living space of the home. Again, make sure it's the outside dimensions. Multiply this total by 3 volt amperes. This is the total general lighting load for the home. Here's an example that uses figure 12-3. The total area is 2100 square feet. Multiply 2100 square feet by 3 from table 220.12. The total volt amperes required by general lighting and receptacles equals to 6300 VAs. The NEC requires that 2 small appliance circuits, each having a load of 1500 volt amperes, for a total of 3000 VAs. 2 1500 volts or 1500 VA small appliance loads equals 3000 VAs again. A separate laundry circuit of at least 1500 VAs is required by the NEC. If the rating on the equipment's nameplate is higher, use that number instead of the 1500 VAs. Again, the load for one laundry circuit equals to 1500 VAs. The laundry load and small appliance load may be added to the general lighting load prior to applying the demand factor. The demand factor is taken from table 220.42, and this reduces the load as follows: general lighting load plus small appliance load plus laundry load, in this case equaling 10,800 VAs. The first 3000 VA is applied at 100%, which equals to 3000 VAs. Then the remainder is applied at 35%. The remainder is applied at 35%, which is 7800 times 0.35, which gives us 2730 VAs. The total general lighting load is 5730 VAs. Appliances. The load for specific appliances is based on the ampere rating specified on the nameplate of the appliance. Demand factor. Again, the demand factor of 75% can be applied only if there are 4 or more of these appliances on one feeder or service. This category of appliances does not include electric ranges, clothes dryers, space heating equipment, or air conditioning equipment. For example, dishwasher equals 1800 VAs, water heater equals 3800 VAs, garbage disposal equals 972 VAs, and the total appliance load would be, in this case, 6572 VAs. Clothes dryer. Find the total of the clothes dryer by looking at the nameplate. If this rating is less than 5000 volt amperes, you must use 5000 in the calculations. If the load on the nameplate is higher, use that number. Unless there is more than one electric dryer installed in the home, a demand factor cannot be used. Table 220.54. This dryer is 240 volts, 27 ampere unit. So 240 volts times 27 amperes equals 6480 VAs. So the total load for the clothes dryer is 6480 VA. Determining the number of branch circuits. Having the proper number of branch circuits on a system will prevent unsafe overloading of the circuits and the nuisance of tripping breakers. Now that you're able to calculate the branch circuit load, it is time to divide the loads into safe and convenient circuits. Article 210 of the NEC outlines the rules regarding the general provisions and specific requirements for branch circuits. These rules, when followed, will certainly provide the safe wiring of the branch circuits. Bathroom circuits. Due to the temperature and moisture changes that often occur in bathrooms, circuitry for this area warrants special consideration and discussion. The NEC requires that the bathroom be equipped with a switched controlled lighting fixture and a GFCI protected receptacle outlets adjacent to the basin. Figure 12-4 shows a typical floor plan of a bathroom indicating the electrical fixtures. Each vanity is equipped with a soffit type fluorescent light to eliminate the mirror and a GFCI receptacle for shaving and hair blow drying. In addition, recessed lighting fixtures are installed in certain locations to ensure adequate lighting throughout the bathroom. The heater fan light device is another convenient, efficient, and practical item worth consideration. Small appliances. There must be a minimum of two 20 ampere circuits dedicated to receptacles for small appliances. This circuit load can be included with the general lighting load as stated in section 220.52a. These receptacles are located on walls and floors and are used primarily for kitchen appliances. See figure 12-5. Also required is at least one 20 amp to 120 volt outlet in the laundry area. Refer to Article 220 of the NEC for specific rules on these circuits. Also review the tables and examples in Chapter 9 of the NEC. Laundry. The laundry equipment will use a 20 ampere circuit that has no other receptacles. These circuits can be included with the general lighting load as stated in section 220.52b. Wire capacity. Although the NEC specifies 14 AWG as a minimum wire size, it would indeed be unwise to use anything smaller than 12 AWG in homes built today. Lighting and receptacle outlets wired with 14 AWG will almost certainly be inadequate in 10 to 20 years. Keep in mind not only for lighting and receptacle load considerations, but also for all future calculations for proper wire ampacities. See the NEC table 310.15b16. Very important table. 310.15b16. Wall switches. All lights should be controlled by a switch located near each entrance in a room. Wall switches should be placed in locations that are accessible and at height suitable for all occupants. Generally, wall switches are 48 inches to 52 inches above the floor level and on the latch side of the doorway. See figure 12-6. Article 404 of the NEC describes additional installation requirements. The Americans with Disabilities Act, or ADA, a comprehensive civil rights law for people with disabilities, stipulates that the height of wall switches to follow these rules. If the clear floor space allows parallel approach by a person in a wheelchair, the maximum high side reach allowed shall be 54 inches. If the wall switch must be accessed by reaching forward, then the maximum height shall be 48 inches. An important website is www.ada.gov/stdspdf.htm, which is the Americans with Disabilities Act, or ADA, which was passed in 1990, gives civil rights protections to individuals with disabilities. This website contains guidelines for making public areas accessible. At a minimum, you should read the section regarding switch and receptacle heights. Following these guidelines will help you create a house that can accommodate a wider range of homeowners. Outlet receptacles. The NEC requires that receptacle outlets be provided in kitchen, family room, dining room, and living room, parlor, library, den, sunroom, breakfast room, bedroom, recreation room, and other similar rooms in a dwelling. Receptacle outlets must be located so that no point along any wall space will be more than 6 feet, that's 183 millimeters from a receptacle. This rule applies to wall spaces 2 feet or wider, including outside wall spaces occupied by sliding panels. Where fixed room dividers or freestanding counters add to the wall space, the same 6-foot rule applies. See figure 12-7 for this. Locate the receptacles close to the ends of large wall spaces to avoid concealment by sofas or other large pieces of furniture. Receptacle outlets should be placed 12 to 15 inches above the floor line. Placing the receptacles at height of 15 inches allows for easier access. A receptacle outlet must be installed at each island or peninsular type countertop that is 20 Maximum number of outlets. The NEC does not formally specify the maximum number of outlets permitted for the entire building or even for each circuit. However, the continuous load on any branch circuit is not to be greater than 80% of the circuit rating. The maximum wattage for each circuit, CKT, is found as follows. So the circuit amperage times the circuit voltage equals, or circuit amperage times circuit voltage times 0.80, which is 80%, equals the circuit circuit voltage amperes or circuit VAs. A 20 branch circuit, for example, can have a maximum continuous load of 20 amps times 120 volts times 0.80, which is 1920 VAs. While this is clear cut as far as the total wattage per circuit is concerned, while this is clear cut as far as the total wattage per circuit is concerned, some other considerations must be included in order to determine the number of outlets for each circuit. The load for each lighting outlet can vary considerably, although some lighting fixtures, like fluorescents, draw a constant load, others do not. Most lighting fixtures can accommodate 25, 40, 60, 75, 100, or 150 watt bulbs. The receptacle outlet load is also variable. Some outlets are rarely used. Others may have no more than a small right light or a small night light connected to it. Still others may operate 100 watt table lamps, floor lamps, or portable heaters. Split wiring. Often duplex receptacles are split wired, or one outlet may be controlled by a switch. The upper half of the receptacle is always hot, while the bottom half is switched. This method of wiring is most frequently used in rooms that do not have a ceiling mounted fixture. See figure 12-9. Lighting. The NEC clearly points out that there are certain lighting outlets that are required in dwelling occupancies. Essentially, every room, hallway, stairway, detached garage with power supplied to it, and every entranceway must have at least one wall switched lighting outlet. In addition, the attic, utility room, basement, and below floor crawl spaces, if used to store items, must have at least one lighting outlet that must be wall switched. There are exceptions to these basic requirements. A wall switched receptacle is permitted. A wall switched receptacle is permitted in rooms other than the kitchen or bathroom, where a lamp may provide lighting instead of a wall or ceiling fixture. A remote control switch may be used for hallways and stairs. These basic requirements are shown in figure 12-10. The quality and types of lighting fixtures available are beyond the scope of this book. However, good lighting is essential for personal well-being and should be carefully considered. Good lighting should always provide an adequate amount of light where it is needed. Lighting should not create shadows or glare. You must be familiar with the criteria that go into creating good lighting in order to understand it. The terms such as candle power, lumens, foot candles, and as well as others must be understood to get a real insight into the proper quality of lighting for the home. Lighting fixture installation rules. Article 410 of the NEC deals with fixtures, pendants, arc lamps, discharge lamps, incandescent filament lamps, lamp holders, and the wiring and equipment forming the above lighting and its installation. Non-coincident loads. There are loads that will not be operated at the same time. These are called non-coincident loads. An example is the load created when an air conditioner or furnace is running. These two units would never be on at the same time. In this situation, you would calculate the load to be the higher of the two, not both. The following example compares a central air conditioner to an electric forced air furnace. According to the nameplates on the central air conditioner, 960 VAs According to the nameplate on the central air conditioner, 960 VAs of power is required to cool the house. The electric furnace requires 13,200 VAs of power. Since these loads are non-coincident, you will need to use only the higher of the two loads, which is the 13,200 VAs, when calculating the total power load or the total load of the house. Another example of a non-coincident load may take place in a residential garage or workshop. Most power tools in this situation would be used one at a time. The tool with the largest load would be used to calculate the voltage or the volt ampere requirement. Feeder and service load calculations. A feeder is recognizable by the presence of an OCPD away from the main service panel. See figure 12-11 for this. A detached garage with its own main breaker is connected to the home service panel by a feeder. A kitchen that is located a great distance from the main service panel may have its own feeder. This method reduces the number of conductors that run this distance from many 12 AWG to a few 3 AWG or 4 AWG wires. The total of all branch circuit loads and feeder loads is the service load. Code alert, section 100. All circuit conductors between the service equipment, the source of a separately derived system or other power supply source, and the final branch circuit overcurrent device are called feeders. In this example, we require a feeder to be sent out to the load center in a garage. This feeder will supply 240 volts at 60 amps from two breakers in the main panel. This would provide enough power for lights, receptacles, power tools, and most welding equipment. 240 volts times 60 amps, as seen in the example, equals 14,400 VAs. So the feeder in the garage equals to 14,400 VAs. Now that all branch circuit loads and feeder loads have been calculated, you can determine the service load. This is done by adding all branch circuit loads and feeder loads. As you can see, the total general lighting load equals to 5,730 VA. The total air conditioning load equals to 3,380 VA. Total appliance load equals 6,572 VA. The total load for the clothes dryer is 6,480 VA. The feeder for the garage is 14,400 VAs. So the total service load equals to 36,562 VA. The service to this home will be supplied by a 240 volt single phase 3-wire system. So divide the total service load by the voltage to calculate the amperage required by this home. So 36,562 VA divided 240 volts equals to 152 amp. This home will need a minimum of 152 amp to operate safely. Round this up to the next standard size main breaker and you would install a 175 amp panel. So before settling on this size, you may want to consider other factors such as: is there a good chance that the home could be expanded? Will the homeowner build a workshop in the future? What size service is installed in the neighborhood homes? Is the service large enough to handle the addition of a pool or hydro massage bathtub? With these possibilities in mind, it may be a good idea to upgrade the service to a 200 amp. This will leave plenty of power available for the future. Optional feeder and service calculations, or optional feeder and service load calculations. Part 4 of Article 220 contains rules for using an optional method that requires fewer calculations to determine feeder and service loads. This easier method may be used if the residence is serviced by 120/240 volts or 208 Y/120 volt set of 3 wire service or feeder conductors with an ampacity of 100 or more. Since this situation covers many new home installations, the optional method is frequently used. The previous examples will be used for the optional calculations so that ease of use and service load results may be compared. General loads optional method. Each of the following 4 categories must be calculated and then added together. Subtract 10,000 VA from this total before multiplying it by 40%. Add the 10,000 VA back to that product to arrive at the total general load. 1. As you can see the steps on your screen, the general lighting and the general use receptacles. Multiply the total square foot or square feet of living space by 3 VAs per foot squared. This is from section 220.82b1 from the NEC. In this case, we're looking at 2100 feet squared times 3 VAs divided by, or times 3 VA per foot squared, which gives us 6300 VA. The total volt amperes required by general lighting and receptacles is 6300 VAs for this instance. Step 2, small appliance branch circuits. 2 minimum and a laundry branch circuit. Each 20 amp branch circuit requires 1500 VAs. So 3 times 1500 VAs equals 4500 VA. Total small appliance and laundry circuits equals to 4500 VA again. Step 3, permanently connected appliances. The total nameplate ratings of all appliances described in section 220.82b3. We have in this case a dishwasher 1800 VAs, a water heater 3800 VA, garbage disposal 972 VAs, electric clothes dryer 6480 VAs, and total permanent appliance load, this is the total of all those, is 13,052 VAs. The total general load is calculated as follows. General lighting and receptacles in this case is 6,300 VAs. Small appliance and laundry circuits is 4,500 VAs. The permanent appliance load is 13,052 VAs. General load is 23,852. That's added. That's all of those above added. Gives you 23,852 VAs. So you subtract the 10,000 VAs from that, from the 23,852, and we get 13,852 VAs. And we multiply the remainder by 40%. We get 5,541 VAs. Once again, we add 10,000 VAs to the product, and we get a total general load of 15,541 VAs. Heating and air conditioning load optional method. Select the largest of the following 6 calculations to use for the heating and air conditioning load. 100% of the nameplate rating of the air conditioner, 100% of the nameplate rating of the heat pump when the heat pump is used without any supplemental electric heating, 100% of the nameplate ratings of electric thermal storage and other heating systems where the usual load is expected to be continuous at the full nameplate value, 100% of the nameplate rating of the heat pump compressor, and 65% of the supplemental electric heating for central electric space heating systems if the heat pump can operate at the same time as the supplementary heat. 65% of the nameplate rating of electric space heating if less than 4 separately controlled units. And 40% of the nameplate rating of electric space heating if 4 or more separately controlled units. The air conditioner in the example qualifies for the first calculation in the above list, which is, in this case, 100% of the nameplate rating of the air conditioner. So add the air conditioning load, the general load, and the garage feeder load to determine the service load. In this case, we get 15,541 VAs plus 3,380 VAs plus 14,400 VAs, which gives us the total of 33,321 VAs. So that is the service load, 3,321 VAs. The service for this home will be supplied by a 240 volt single phase 3-wire system. So you have to divide the total service load by the voltage to calculate the amperage required by this home. In this case, 33,321 VAs divided by 240 volts equals to 138 amp. So based on the optional method, a 150 amp service is all that is necessary for this residence. Again, review the previous factors that may justify upgrading the service to a higher amperage before settling on the calculated service. Just as a side note, your calculated service amperage size for your OCPD or your main breaker, it is not so much as the protection for the panel, but the amount that you envision the house to be limited by. The limits, that is basically the limit of amperage that you would like the home to have. Each circuit, each branch circuit should have its own OCPD or overcurrent protection device, and those are the ones that protect the house and the equipment and the persons living in the house from the effects of overcurrent, fire, overheating, and damage. Not so much the main breaker. The main breaker is your upper limits, and it does also play a safety factor, it has a safety factor to limit the amount of current that enters the house, but it could be a bit higher if you so wish for it to be. The limit could be a bit higher to accommodate future expansion in the electrical use or future increases of electrical use. Balancing circuit loads. When planning the hookup of branch circuits and feeders to the main service panel, it is important to keep a balance in the load between the two hot wires and a three-wire system. Remember that the neutral wire in this system is carrying the unbalanced electrical load from both hot wires. Again, remember that the neutral wire in this system is carrying the unbalanced electrical load from both hot wires. Looking at figure 12-12, it helps explain what is happening as the current flows through the system. The alternating currents in the two hot wires does not flow in the same direction at the same time. At the instant it flows in one way in the red wire, it is flowing in the opposite direction in the black wire. At the same time, the flow for each wire will change in the neutral wire. The two currents flowing in opposite direction through the neutral wire tend to cancel each other's inductance. As long as the current in each direction is nearly equal, there is no problem. However, when the current differences are great, there may be trouble. The neutral wire may heat up, or the neutral wire will heat up, and the insulation could melt. This situation can arise with appliances that operate on both 120 and 240. These appliances must be evenly balanced between the two hot wires to reduce the likelihood of overloading the single neutral conductor. Looking at figure 12-13 shows a system properly balanced at the entrance panel. If you add up the ampere rating of all the circuits on each side, you can see that the ratings add up to nearly the same total. Also, the same number of large appliance circuits is found on each hot wire. Figure 12-14 shows a typical entrance and hallway. We shall see if fixtures and receptacles for these areas can be placed on a single 15 amp branch circuits. The following outlets and fixtures are needed. This total does not exceed the maximum allowable load for a 15 amp branch circuits. 15 amp times 120 volts times 0.80 equals 1440 VAs. The hallway and the entrance can be placed on the circuit with a 15 amp overcurrent protection device. Moving on to the review questions for this chapter. Number 1, fill in the blank. I will go ahead and state each question as a complete statement with the answer already inserted. As you can see, some of those are clearly marked on the screen. The total electrical load requirement must be calculated before determining the number of circuits for a house. The general lighting load covers small appliances, laundry units, bathroom requirements, and most receptacles throughout the home. The NEC requires at least 2 small appliance circuits. Loads that will not be placed on the system, and again, loads that will not be placed on the system at the same time are called non-coincident loads. Where should you look to find the ampere rating of an appliance? The answer is at the nameplate or label of the appliance. A group of 2 4 AWG wires, one black and one white, running from a main service panel to a smaller service panel near the kitchen is a feeder. True or false? The receptacles in the laundry room can be placed on the same circuit as the kitchen. That is a false statement. It is important to balance the loads when connecting the circuits to the service panel. List 3 locations where GFCIs are required. Those are bathrooms, laundry rooms, outdoors, or in garage and basement. Counter spaces in kitchens wider than 2 feet require a receptacle outlet. And lastly, a true or false question: if a garage has electricity, it must have a ground fault circuit interrupter, or GFCI. The answer for that is true. For the section of Know the Code, which is a section that helps you be familiar with the NEC by looking up some answers for questions, is the following. Number 1, what section requires at least 1 receptacle outlet in the laundry area, and how many exceptions are in this section? And the section is the 210.505F. Again, 210.55F. And there are 2 exceptions if you look this section in the NEC. Number 2, where is the NEC, or where in the NEC can you find examples of branch circuit load calculations? And as far as I know, there are some in table 220.3A and 220.3B 1 through 11, and you can verify, make sure that it's correct. Finally, question 3, which article covers feeders? That is article 225, outside branch circuits and feeders. That is the title of that article. Thank you very much. This wraps up and concludes this chapter, chapter 12. And good luck with the rest of your studies. Please continue on until you master and or finish this course. Thank you very much.